What's up, everybody, and welcome back to OpenStax Algebra and Trigonometry, Chapter 10, Section 1, Non-Right Triangles, Law of Sines. Let's do it. Question number 1, describe the altitude of a triangle. So before I describe it, let me draw one out and show you what it looks like, and then I can explain it. So let's say we have a triangle like this. An altitude would be a line that I could extend from a single vertex. Let's take the top one. And that comes down and touches the opposite side, but it touches it in a very particular way. It hits it at exactly 90 degrees. So it's perpendicular to the opposite side. So that would be an altitude. Now, there are altitudes for every single vertex, right? And I could draw one down from this one and this one across. But there is something to note that is kind of interesting. Sometimes altitudes will be external. So for example, in this case, I've drawn an altitude, but it happens to be an external altitude that would be perpendicular if this line were extended out further. But that's the gist of it. That's the definition. Done. So this question asks when you can use the law of sines to find a missing angle. So let's take it like this. Instead of kind of explaining it in an abstract sense, let me give you an example. Let's say we know one angle. Now, the key with the missing angle is if you know two angles, you can find the third. So let's assume we only know one angle. Let's say this one is 42 degrees. Then let's say we're trying to find angle C. Let's call that X. In order to execute the law of sines and to find angle X, I need to know both the side opposite the 42, let's pretend that is 10, and then I also need to know the side opposite X, let's pretend that's 6. I'm just making it up. And then we can use law of sines. And by the way, if you're not sure, try it, right? Because law of sines is sine of an angle over the opposite side equal to sine of an angle, a different angle, over its opposite side, right? And if you don't have all the components, you can't do it. So you can always try it out and see, but that's the gist of it. That's how you do it. Boom, done. What type of triangle results in an ambiguous case or could result in an ambiguous case, right? So the idea is when you know two sides, let's say this side is 10 and this side is 8, and then I'm given not this angle, but one of the other two. Let's say I'm given this one and it is 55 degrees. In this case, it could potentially be two triangles. This is the ambiguous case. And the other way to remember it is if what's given to you is an angle, a side, and a side, right? As opposed to if I had 32 degrees in here, then this is side, angle, side. Then that angle is included between those two sides, within those two sides. So that would not be an ambiguous case. But this one is, again, angle, side, side. That's how you do it. Done. So for this one, it says to solve each triangle, meaning solve for every missing angle inside. So first, let's draw it out. And again, this triangle is not to scale by any means, but it's just something to use that we can visualize with, right? So I'll make angle 35 here just because it does look like the smallest angle. I'll make 73 occur over here. And then it says that side C is opposite this gamma angle, so I'm going to put 20 over here. The unknown side here is beta, or angle, I should say. So first, let's find angle beta. And that can be done using the triangle angle sum theorem, right? 35 plus 73 is 108. So the missing angle must be 72 degrees because all the angles have to add up to 180. So we know beta. All right. Now we need to find side A and side B. All right. So to do that, I'm going to use my law of sines. So I'm going to say, let's find A first. Sine of 35 over the opposite side, which is A, is equal to, let's just do this one because we have to, because we have to do it with one that doesn't have a variable, right? So then that's equal to sine of 73 over 20. Okay, now we're going to cross multiply like so. We get A times sine 73 equal to 20 sine of 35. And then we're going to isolate and divide both sides by sine of 73. And to get this value, we're going to approximate in Desmos. Make sure that you're in degrees mode first. And we get 11.995, which rounds up to 12.0. And then for B, we're going to do the same thing. I'm going to say sine of 72 over B equals sine of 73 over 20. Now, I could have said sine of 35 over this, but I like to avoid that because this is an exact value. This is an exact value. This is an exact value. So I'd like to go with things that are exact values when I have the choice. So then let's cross multiply. And I get B sine of 73 equal to 20 sine of 72. Last step, we're going to divide both sides by sine of 73, and we'll see what that is in Desmos. And here we get 19.89 rounded up to 19.9, which means that B equals 19.9. So here are our three answers, A, B, and beta. Boom, done. So for this one, I got a generic triangle set up, and I'm just going to fill in what we know. Beta is 100, alpha is 60, and A, which is opposite alpha, is 4, okay? And then so what we're trying to solve for are C and B, and then also angle gamma. Now, gamma is pretty easy, right? Because we can use the triangle angle sum theorem. Everything has to add up to 180, so if that's 60, that's 100. This has to be 20 degrees. And then now let's use the law of sines to solve for the remaining sides. So let's start with sine of 60 over 4 is equal to, let's solve for B first, sine of 100 over the side opposite, which is B. Okay, we're going to cross multiply. We get 4 sine of 100 equal to B sine of 60. Then we're going to divide both sides by sine of 60 like so, and then we're going to see what that is in Desmos. And we get approximately 4.5 rounded to the nearest tenth, so B equals 4.5. Now let's run it again, trying to solve for C. So we're going to say sine of 20 over C, right? Sine of this angle over the opposite side is equal to sine of this angle over its opposite side, sine of 60 over 4. Now we're going to cross multiply like so. 4 sine 20 equals C sine of 60. And then we're going to divide by sine of 60 like so. Let's plug it into Desmos. And we get rounded to the nearest tenth, 1.6. So that means that C equals 1.6. So those are the three missing values, 4.5, 1.6, and then of course 20 degrees, boom, done. So for this one, we're given that A is 37 degrees, B is 49 degrees, and this side C is 5. And again, C is going to be opposite the angle C. So this side here is 5. And what we're trying to find is side B, and that's opposite angle B like this. All right, so what we need is we need to set up the law of sines. But the problem is to do that, since the only side length I have is this, I need this angle. And I can figure that out using the 180 sum theorem, right? Triangle angle sum theorem. So all three angles must add up to 180, and since 37 plus 49 is 86, this must be 94, because 94 plus 86 gets us back to that 180. Now I can set this up. So I got sine of 94 over 5, because that's the opposite side, is equal to sine of 49 over B. And again, I have to choose 49 because it's opposite the side that we're trying to find. Okay, now we're going to cross multiply like so, and I got 5 sine of 49 equals B sine of 94. Then I'm going to divide both sides by sine of 94. Let's write it down here. B equals 5 sine 49 over sine of 94. Let's plug that into Desmos. And here we get 3.78 to the nearest hundredth. So B equals 3.78. Boom, done. So for this one, I'm going to plug in the values 37 here for B, 21 for C, and then B is 23. And again, little b is opposite big B, so this is 23. Now, we need to use law of sines, and we're trying to find side C, which is over here. And we already have the information we need, right? We can use law of sines as is without even finding this angle, because I can start with sine of 37, this guy, over the opposite side equals sine of 21 over x. And the reason why we're choosing 21, of course, is because it's opposite x, right? Little c is opposite big C. Now we're going to cross multiply, and we got x sine of 37 equal to 23 sine of 21. And then we're going to divide both sides by sine of 37, and we got 23 sine 21 over sine 37. Let's plug it into Desmos. And to the nearest hundredth, we get 13.70. So C equals 13.70. Boom, done. So for this one, we're going to follow along with the ambiguous case for triangles infographic, and we're going to set the triangle up. So we got it like so, right? The side C is opposite gamma, little b is opposite beta, and so on and so forth. Okay, so check this out. We've got side, angle in that order, which means there theoretically could be two triangles. There could be one triangle. There could be no triangle. All right. So let's see how we can figure this out. First, we want to solve for this missing angle here, beta, because it's opposite this known side. So let's set it up. So we have sine of b over 10, right? Because those two are opposites of each other, equals sine of 113 over 32. Now we're going to cross multiply, and we get 32 sine of b equal to 10 sine of 113. Now to solve for b, we're going to divide both sides by 32, and then we have sine of b equals this. So to find this value now, we have to do the opposite of taking sine, which is taking arc sine. So b then equals arc sine, like so, of that whole value, 10 sine of 113 over 32. So what we're going to do is we're going to figure this out in Desmos. So now we get an angle of 16.7. So beta equals 16.7 degrees. Now we got to figure out, do we have one triangle, two triangles, or no triangle? So what we're going to do is we're going to take this new angle, right? Just like they have here, we take this new angle that we just solved for and we subtract it from 180. So we're basically finding what's supplementary to this 16.7. And we get 163.3. So now when I take this new angle, 163.3, just like we're doing right here, I add it back to the known angle and I see, what do I get? Well, in this case, I get something bigger than 180. I get 276 something, right? It's like a big value. So when it's greater than 180, then we know we're in the one triangle zone. So there's only going to be one triangle, not two triangles, not no triangle. So then we know that this angle here is going to be 16.7 degrees. And then the remaining one from triangle angle sum theorem is going to be 50.3 degrees, right? Because then they all add up to 180. Now the last side we have to solve for is side A. So we're going to, again, use law of sines one more time. So I got sine of 113, which we're already given, over its opposite side, 32, is equal to sine of 50.3 over its opposite side, which is A. Now, when we cross multiply, we get 32 sine of 50.3 is equal to A sine of 113. And then last step, we divide both sides by sine of 113. And then let's plug that into Desmos. And we get 26.7. So therefore, A equals 26.7 rounded to the nearest tenth. So the three missing values are this. Then we got this angle beta, and then we got this angle alpha. That's how you do it. Done. So for this one, we'll start by setting it up. We got alpha, beta, and gamma, and then we've got 35 is alpha, 35 degrees, and then we got A, which is opposite alpha, is 12, and C, which is opposite gamma, is 17. So again, this is another side-side angle. This could be two triangles, one triangle, no triangle, so we got to figure that out. All right, first things first. The first angle that we can find is going to be gamma because we have a known side opposite gamma. So let's set that up now. Sine of gamma over 17 is equal to sine of 35 over 12. Now we're going to cross multiply. We get 17 sine of 35 equals 12 sine of gamma. Then we're going to divide both sides by 12. And then the last step to isolate gamma is to get rid of that sine. And the way we do that is we take arc sine of both sides. That's going to basically get rid of the sine, and then we're going to be solving for gamma. Let's plug that into Desmos now. So here we get 54.35, or rounded to the nearest tenth is 54.3. And now we're going to test to see whether or not we have two triangles, one triangle, or no triangle. Well, we definitely have one triangle at least, right? This is viable. Now, to see if this is legit, what we're going to do for two triangles is we're going to subtract that new angle that we just got from 180, basically finding what's supplementary to this. And what we're going to get is 125.7. Now, what we're going to do now is go back to the given angle that we have, which is 35 degrees. And we're going to say, what is 35 plus 125.7? Is it less than 180 or greater than or equal to 180? It's less than 180. So guess what? We're in this category. We do have two triangles. Very interesting, right? So now we're going to draw the second triangle. And again, it still has to have the angle of 35 degrees. Now, I know the two triangles are actually not going to be looking the same. They're different, but I just draw it the same because I feel like it's easier from a consistency standpoint to just go ahead and solve the two triangles this way. So just bear in mind that this is not an accurate representation. But anyways, we got 35. Then what's the new gamma or the different gamma in this triangle? It's this. It's this little supplementary angle that we already calculated. So then this pops up here. And the sides can't change, right? Those are fixed as well. So this still has to be 12. This still has to be 17. Now we can solve for each of these remaining triangles. So in this one, we got 54.3, 35. The missing angle, therefore, since these two add up to 89.3, is going to be 90.7. Just a little above 90, because then those will add up to 180. And now we're going to solve for this missing side. And well, actually, let's get this angle first. So since these two add up to 106, 60.7. The remaining angle here is 19.3 degrees. So now just moving that infographic off to the side to make a little bit of room, we need to first solve for this side. So let's do sine of 90.7 over little b, which we're trying to solve for, equals, and then let's do this one, sine of 35 over 12. I always like to go with the ones that were like given at the beginning because they're nice whole numbers. We're not rounding, so it's the most accurate as possible. Cross multiply, we get b sine of 35 is equal to 12 sine of 90.7. And then we're going to divide both sides by sine of 35. And to get b, let's plug that into Desmos. And here we get 20.9. So b equals 20.9. So this is one triangle solved. Now we got to finish solving this one. We got the three angles. We got two sides. We just have to find this missing b here. So again, using law of sines, sine of 19.3 this time over b equals, and then we have the same thing, sine of 35 over 12. We're going to cross multiply. We're running out of room. These are long problems. Then we got b sine of 35 equals 12 sine of 19.3. Last step, we're going to divide both sides by sine of 35, sine of 35, and then b will equal this. So let's plug it into Desmos, and we get 6.9. So b in this case is 6.9. All right, so here are all the answers, right? Here's b in this one, here's the gamma in this one, and here's angle beta in this one. And then for this one, here's the other gamma, here's the other little b, and here's the beta. That's how you do it. Two triangles, done. So for this one, I'm going to start off by actually drawing two triangles. We're going to see if there actually are two triangles. We still have to run the test. And if there's not, right, I just cancel it out. But we just have it set up like this. And again, both of them, alpha is 43. In both of them, little a across from alpha is 7. And for both of them, c, which is opposite gamma, is 9. All right, so for the first one, we're going to solve for gamma because it's opposite the known side. And so we got sine of 43 over its opposite side, 7 is equal to sine of gamma, which we don't know, over the opposite side, which is 9. Now we're going to cross multiply like so. We got 9 sine 43 equal to 7 sine gamma. And now to solve, we're going to divide by 7, get rid of that. And then we have to take arc sine of this quantity, right? Because that's how we do the opposite of sine, is take arc sine. And by the way, right, take an arc sine of sine, it just gets rid of the sine. So now we have gamma equals this. Let's plug it into Desmos. And we get 61.3. So here we have 61.3 degrees. All right, now we have to run the test, right? So what we do following this step is we've just found our C, right? A, B, C, it doesn't matter, right? But we found an angle. So now we're going to find the supplement, aka subtract it from 180. So 180 minus 61.3, that happens to be 118.7. Okay, so the question is 118.7 plus this known angle of 43, is that less than 180 or greater than 180? And when we add it together, we get 161.7. And guess what? That's less than 180. That means, whoops, not that one. Sorry. We're actually in the two triangle situation, right? Because it's less than 180. Beautiful. And the other awesome thing is now this supplementary angle that we found, 118.7, this is what's in play in the second triangle, which means while gamma is 61.3 here it's 118.7. So that slides in nicely. And now we can find the remaining angles by triangle angle sum theorem. For this one, it's got to be 75.7. If you're wondering why, think about adding these up. That would be 104.3. 104.3 plus what gives you 180? It's got to be this. And then over here, we already know that those two angles add up to 161.7. So what makes this up to 180? If we add, it would be 18.3. All right, now all we have to do is solve for little b on both of these triangles. So let's use the law of sines one more time. I'm going to get rid of this infographic. I'm going to move it over. So for the triangle on the left, we've got sine of 75.7 over b equals, and I'm going to use the given one again, sine of 43 over its opposite side, 7. So once we cross multiply, we get b sine of 43 equal to 7 sine of 75.7. Then we're going to divide by sine of 43 on both sides. Okay, and let's plug that into Desmos. And we get 9.9. So B in this triangle is 9.9. Now we're going to do the same thing with this triangle, and we're going to use law of sines. So we got sine of 43 over 7 is equal to sine of 18.3 this time over B. And then we're going to cross, and we get 7 sine of 18.3 equals B sine of 43. Sorry, I know this is not lining up nicely, but then last up we divide both sides by sine of 43, and we get B equals 7 sine of 18.3, right? I'm dividing both sides by the sine of 43, so we just get sine of 43 underneath. Let's plug that into Desmos. And here we get 3.2. So for this triangle, it would be 3.2. So these are our answers. 3.2 for this triangle. These are the new angles, right? 118.7 to 18.3. And then for this one, the angles are 75.7, 61.3, and the new B value for the side is 9.9. That's how you do it. Done. So this one, we got the setup with the two triangles, just in case there are two triangles, right? We don't know, we have to test for it, but in case, we got the setup. All right, now let's begin by solving for beta. So why am I solving for beta first? Because I have the side opposite it, and then I have these two together, so let's do that now. So we got sine of 10 over 5 is equal to sine of beta over 13. All right, we're going to cross multiply, and we got 5 sine of beta is equal to 13 sine of 10. And then we're going to divide both sides by 5 first, and then to find B, we have to take arc sine of this whole expression, right? The opposite of sine. So we got arc sine of 13 sine 10 over 5. And to calculate this, let's plug it into Desmos. And here we get 26.8. So in this triangle, we'll have 26.8 degrees. And then we can figure out from the triangle angle sum theorem, the remaining angle would be 143.2. So how did I get that? Because 10 plus 26.8 is 36.8. And to get up to 180, which is, right, the triangle angle sum theorem, to get to 180, we need to have a remaining 143.2. But you could use a calculator if you need to verify that. Now we need to see if there is one triangle, two triangles, or no triangle. So we're going to take this beta value here, and we're going to subtract it from 180. And we get 153.2. So the reason why I highlighted these two in blue, by the way, these are the given angles, right? So this is not changing. So, and then I also need that given angle just like I do up here, right? I take that given angle of 45 and I add it to this new angle. So 153.2 plus 10, guess what? It is less than 180. It's not, if it was greater than 180, then we'd be in the one triangle situation, but we're less than 180, which means this is in the two triangle situation. So we do have two triangles. And the nice thing about this step, when we do the subtraction from 180, this angle that we get here is the second beta value, is the beta value in this triangle. So this is 153.2. And then we can use the same triangle angle sum theorem to find this missing angle, right? If that's 10, that's 153.2. That adds up to 163.2. Hence, this side is going to be this angle is going to be 16.8 degrees. Now we have to find the final side, which is A. In both of these, I'm going to move this over and make some room. So using law of sines in the first triangle, we've got sine of 10 over its opposite side, which is 5. I always like to start with the given set that they give us because those are nice exact values, equals sine of, now we need to find this, so we're going to use this angle, sine of 143.2 over the opposite side, which is A. Now we can cross multiply. 5 sine of 143.2 equals A times sine of 10. And then to solve for A, we divide by sine of 10, like so. And let's plug that into Desmos. Now we get 17.2. I know in the back of the book they have 17.3, but I'm going to roll with what we got here. So 17.2. And then now to solve for this A, we're going to again use law of sine. So similar setup, right? Sine of 10 over the opposite side 5 equals, in this case, sine of 16.8 over A. We're going to cross multiply like so. Then we have, I'm going to go down here, 5 times sine of 16.8 equals A times sine of 10. Last step, we divide both sides by sine of 10. We're going to plug that into Desmos now. And here we get 8.3. So here A is 8.3. So The remaining angles in the first one are 26.8, 143.2, and the new side is 17.2. Again, they have 17.3 in the back of the book, but and the process is identical. And then for this one, it's 16.8 for that alpha, for this beta, 153.2, and 8.3 for the other A. 2 triangles, boom, done. So for this one, again, I'm starting under the assumption that there could be 2 triangles, so I've drawn them out. But again, this could be a 1 triangle situation, a no triangle situation. So anyways, we got this set up. We got the side angle. And let's start with law of sines to see if we can figure out this angle alpha. So we have sine of alpha over 11.3. And again, I put A here because A is supposed to be opposite alpha, little b is supposed to be opposite beta, etc. Okay, so we have sine of alpha over the opposite side equals sine of 119 over that opposite side as well. Now we're going to cross multiply. We got 11.3 sine of 119 equal to 8.2 sine of alpha. And then we're going to divide by 8.2 on both sides. Boom, boom, cancel. And then to solve for alpha, we need to take the opposite of sine to isolate it. So we're going to take arc sine of the other side like so, and let's plug that into Desmos. Now the thing is, before I even apply arc sine, I see that the argument for arc sine is greater than 1. That is outside of the domain of arc sine. That means no triangle exists. But I'm going to show you just what happens when I type in arc sine. So you see we get undefined. So that means the triangle does not exist. So this is a no triangle situation. That's how you do it. Done. So for this one, we're going to start with the assumption that it could be 1, 2, or no triangles. So we just kind of have this set up just in case. Now we're going to start by solving for angle A. That's because we have that opposite side there. So we can say sine of A over its opposite side, 13, is equal to sine of 20 over that opposite side, which is 6. Then we can cross multiply. We got 6 sine A equal to 13 sine of 20. Then we're going to divide both sides by 6. And then to further isolate it, since we got sine of A, we got to do the opposite of sine, which is take arc sine. So we're taking arc sine of 13 sine 20 over 6. Let's plug that into Desmos now. And we get 47.8. So A will be 47.8 degrees. And I'm just highlighting 20 just to note that those are the given angles. Those angles have to be in one or both of the triangles. That can't change. Now what we do is we take this new angle and we subtract it from 180 and we get 132.2. Then we take this and we add it back to the original and we say, hey, is that less than 180? It is. It would be 152.2. So when it's less than 180, we're in this situation. We have 2 triangles. So what that means is this value here that we got from subtracting from 180, that is the angle A in the second triangle. Now, of course, that doesn't look like a 132.2 degree angle. I just always find it easier to draw the angles identical so we can easily match it. Like, I don't try and draw it to scale. This will work just fine. So since this is all it's asking, it's not asking us to solve the rest of the triangles. Here are the 2 answers. Angle A is either 47.8 or 132.2. Boom, done. So for this one, we're meant to find the area, and I've got this infographic up here that shows you how to do it. So you basically take sine of this angle times 1/2, and then the 2 sides around that angle. So we have that same situation here. The area is going to be 1/2. X and Y are these 2 sides, so 5 and 6, and then multiply that by sine of 35, that angle in the middle. So let's calculate that. And we get 8.6 to the nearest 10th. So 8.6 is the answer. Boom, done. So for this one, once again, we got the formula up here, and we just simply take 1/2 A times B, or X times Y, which is 24 times 32, and then times the sine of that angle in the middle, times sine of 75. Let's plug that into Desmos. And we get 370.9. So 370.9, boom, done. For this one, we're meant to find the length of side X, so we're going to do that now. We're going to use the law of sine. So I got sine of 70 over opposite, which is X, is equal to sine of 50 over the opposite side of that, which is 10. Then we're going to cross multiply. We got 10 sine of 70 equals X sine of 50. Last but not least, we're going to divide by sine of 50 on both sides to isolate that X, and we're going to plug that into Desmos. And we get 12.26 rounded to the nearest 10th is 12.3. So it is 12.3, boom, done. For this one, we're going to solve using law of sine. So we got sine of 45 over what we're trying to find. The opposite side, x, is equal to sine of whatever angle this is over its opposite side, 15. Now, in this case, they actually didn't give us sine of this angle. And we can't use this angle because it's not opposite a known side. So we can figure this out by using the triangle angle sum theorem, which says that all angles in a triangle add up to 180. So this is 75, that's 45. You add them together and you get 120, which means that this remaining angle is 60. So we got 60 up here. Now let's cross multiply and solve. So we got sine 45 times 15 equal x sine of 60. And then we're going to divide both sides by sine of 60. And let's plug that into Desmos. And we get 12.2. So x equals 12.2. Boom, done. For this one, we're going to use law of sines once again. So we got sine of 42, which is this angle, over its opposite side, which is 14, is equal to sine of 50, which is this angle, over its opposite side, which is x. So now we can cross multiply x sine 42 equals 14 sine of 50, and then we divide both sides by sine of 42. Boom, boom, and then we plug it into Desmos. And we get 16.0. So x equals 16.0, boom, done. So for this one, we're going to again use the law of sines to find now a missing angle, but it's the same idea. Sine of an angle over its opposite side, which would be 10 in this case, is equal to sine of another angle in the same triangle over its opposite side, which is 5. All right, now we're going to cross multiply. We got 10 sine of x equal to 5 sine of 98. And then we're going to divide both sides by 10. And then we got sine of x equal to this quantity. So now to get rid of the sine, we have to do the opposite of sine, which is taking arc sine of both sides. That's going to cancel that sine out. And then we have arc sine of this quantity, 5 sine of 98 over 10. Let's plug it into Desmos. And we get to the nearest tenth, 29.7. So x equals 29.7 degrees. Boom, done. For this one, we're going to again use the law of sine. So I'm going to start with sine of an angle over its opposite side, which is 5, is equal to sine of another angle, this is our unknown, over its opposite side, which is 13. Now we're going to cross multiply like so. We got 5 sine of x equal to 13 sine of 22. Then we're going to divide both sides by 5. And then I got sine of x equal to this quantity. Now to get rid of the sine, I have to take arc sine, which is like the opposite of sine of both sides. That's going to cancel out that sine. And then we have arc sine of 13 sine 22 over 5. Let's plug it into Desmos. And we get 76.9. So we get x equals 76.9 degrees. Now, this could be an ambiguous triangle case, right? Because think about it, we have side, side, and angle. So now to figure out if this is indeed an ambiguous triangle, meaning there's 2 and there's 2 possible values for x, we have to subtract this new angle from 180. And that's going to give us 103.1. And then the question is 103 plus 0.1 plus 22, is that less than 180? It is. That means that we do have a second triangle and we do have a second value for x, which is this value. So we have 2 values for x. We have 103.1 degrees or 76.9 degrees. That's how you do it. Done. So for this one, let's start with law of sines. Again, we got sine of 55 over its opposite side, which is 21, is equal to sine of x over 24. Then we're going to cross multiply like so. We have 24 sine of 55 equal to 21 sine of x. Now to isolate x, we're going to divide both sides by 21, boom. And then to get rid of that sine, we have to take arc sine of both sides. So now x equals arc sine of 24 sine 55, over 21. Let's plug it into Desmos. And so what we end up with is 69.4. So x equals 69.4. But here's the issue. It says that x is an obtuse angle. 69.4 is not obtuse because obtuse is between 90 and 180. So this is not an obtuse angle. So perhaps this is a 2 triangle situation. So let's run it through our test. So let's do 180 minus 69.4, and that is 110.6. So now we go back to that same question. 110.6 plus 55, that original given angle, is that less than 180? It is. It's 165.6. So that means there is a second triangle, and that means the second value for x is 110.6. But since it wants an obtuse value for angle x, 110.6 degrees is the answer. Done. So for this one, we're meant to solve for all of the remaining pieces of the triangle. So we got side, side, angle. This could be a two triangle situation, so let's check that out now. We're going to start by solving for angle C. So we got sine of angle B, which is 93, over the opposite side, 32.6, is equal to sine of angle C, which is unknown, over its opposite side, 24.1. Then we're going to cross multiply. We got 24.1 times sine of 93 is equal to 32.6 sine of C. Then we're going to divide by 32.6 on both sides. Boom, boom. And then we got sine of C equals this. Now to calculate C, we have to take arc sine of this quantity. That's like the opposite of sine, so that isolates the C. So we take arc sine of 24.1 sine of 93 over 32.6. Let's plug it into Desmos now. So here we get 47.6. So C equals 47.6 degrees. Now, is there a second triangle? Let's find out. Let's subtract 47.6 from 180, and we get 132.4. The problem with 132.4 is when you add it to the given angle 93, we get something above 180. That means we only have one triangle, so we don't have to worry about that angle. This is the one and only triangle, so let's solve the rest of it. We know that these two angles are 93 and 47.6, so using triangle angle sum theorem, I'm going to add these together, and we get 140.6, which means the remaining angle has to be 39.4 by triangle angle sum theorem. 39.4 plus that gives us 180. Now we have this last side to solve for, little a. So let's do that now using the law of sine. So we got sine of 39.4 over a is equal to sine of, let's do 93 because that was given, 93 over 32.6. Then we're going to cross multiply. And then we've got a sine of 93 equal to 32.6 times sine of 39.4. Last step, to isolate a, we have to divide by sine of 93. I know we're running low on room here, but we got just enough. And let's plug that into Desmos. And we get 20.7. So this side length is 20.7. So here are the three answers. 20.7 for the side length, 47.6 degrees for angle C, and 39.4 degrees for angle A. Boom, done. So for this one, we're going to find the area of the triangle, and it's 1/2 times one of the given side lengths times the other given side length. Again, and they have to be on either side of the known angle, which they are, and then times sine of that known angle. So let's plug it into Desmos. And we get 57.1 rounded to the nearest tenth. So area equals 57.1. Boom, done. So for this one, I'm looking at this side, and the angle in between. I'm not looking at this angle. So we've got 1/2 times 9 times 11, those two side lengths, times sine of that middle angle. Let's plug it into Desmos. And we get 42.0. So the area is approximately 42.0. Boom, done. So for this one, we do area is 1/2 side length, 30, times the other side length, 50, but now we have to take times sine of the angle in between, which is not this angle or this angle, it's this angle. We're not given that angle. So we have to figure it out from the triangle angle sum theorem, because 30 plus 115 is 145. So if those two angles are 145, the last angle is supplementary to 145. It's 35 degrees, so we take sine of 35. All right, let's plug it in. And we get 430.2. 430.2 is the area. Done. So for this one, we're trying to find the length of the diameter here, and the diameter would be double whatever the radius is. Now, since we have this triangle in a circle, that's a radius, which means they're equal, which means these opposite angles are also equal, right? So if this is 110, 110 plus, if I call those angles x, and since they're both the same, 110 plus 2x is equal to 180. So I can figure out the values of those angles. By subtracting 110 from both sides, that's 70, and dividing by 2, that's 35. So these two angles are 35. All right, cool. Now we can use the law of sines to solve for the radius. I can say sine of 35 over the radius, which I'll call x, is equal to sine of 110 over its opposite side, which is 8.3. So now let's cross multiply. We got x sine of 110 equal to 8.3 sine of 35. Next, we're going to divide by sine of 110, like so, and let's plug that into Desmos. We'll see what we get for the radius. And we get 5.06, but this is just the radius. So to get the diameter, I'm going to take this, I'm going to multiply it by 2, and we get 10.1. So the diameter is 10.1, boom, done. So for this one, we're trying to find AD, which is this length out here. So I can do this with the setup I have right now, right? Because I can take sine of 44, and this is out of the larger triangle, right? You notice we have two triangles. We have ABD and ABC, kind of like that slightly smaller one on the inside. But if I take sine of 44 opposite the angle, the side for ABD, which is 12, I can set that equal to sine of 53 right there over AD, my unknown. I'll just call that X. I got an equation. So now let's take it from here. Let's cross multiply. And we got 12 sine of 53 is equal to X sine of 44. Then to isolate X, we're going to divide both sides by sine of 44. Okay, let's plug that into Desmos now. And we get 13.8 to the nearest 10th. So X equals 13.8. Boom, done. For this one, we're meant to find AB in the parallelogram. Again, parallelogram, the opposite sides are parallel and congruent, which means that if this side here is 10, this side over here is also 10. So now I'm looking at this specific triangle, CAB, right? I have enough information for this great triangle because now I can say sine of 130 over 12, that's the opposite side, right? That's that side length in the middle, is equal to sine of B, which we don't know what angle B is, over its opposite side, which is 10. Okay, so now I can start by at least solving for angle B. This is a great first step. So we're going to cross multiply. We got 12 sine of B is equal to 10 sine of 130. Then we're going to divide both sides by 12, like so, boom, boom. And then we have to take arc sine of that side. So we've got B is equal to arc sine, because that's how we get rid of the sine. Do the opposite of sine. That's arc sine of 10 sine 130 over 12. So let's plug that into Desmos. And we get 39.7 rounded to the nearest 10th. So B is 39.7 degrees. Okay, now we can do law of sines again. But first I need to figure out what this angle is here, angle C. Well, if this is 130 and that's 39.7, they add up to 169.7. And all three angles have to add up to 180. That means that this one has to be a little 10.3 degree angle. Now we're going to do law of sines one more time to find AB. So I can say sine of 10.3 over AB, which is we'll call X, that's our unknown, is equal to sine of 130 that was given over its opposite side, which is 12. Now we're going to cross multiply. 12 sine of 10.3 is equal to X sine of 130. And then we are going to divide by sine of 130 on both sides. Boom, boom, like so. And let's plug that into Desmos. And we get a final answer of 2.8 to the nearest 10th. So AB is 2.8. Boom, done. So for this one, it says solve the triangle and round each answer to the nearest 10th. Now, first it says to draw a line that is perpendicular to LM from N. So I'll do that now. And perpendicular means it forms that nice right angle. Now, the reason why we have to do this to solve the triangle is because I have side, angle, side. So normally, law of sines wouldn't be able to do much in this situation. But we can draw a line and then still get to the same spot. So right now we have a 90-degree triangle and here and here. But for this one, it's special because we already know 74 degrees, right? So if that's 74, that's 90. This one has to be 16 to satisfy the triangle angle sum theorem. So we're going to start by solving for this altitude that we just dropped here. So I'm going to say sine of 74 over that altitude, which I'll call X, right, is equal to sine of 90, which is this right angle here, over the opposite side, which is 4.6. All right, so we're going to solve for this value here. We're going to cross multiply, so I got X. By the way, sine of 90 happens to be 1, so if you know that, cool, because then we don't even need it. We can just say 1 times X is just X, is equal to 4.6 times sine of 74. So let's plug it into Desmos. And we get 4.4. So we'll say this side here is 4.4. So the other thing I'm going to do now is I'm going to also solve for this little component right here. Okay, and the reason why is because then I can know what this piece is, and then I can use Pythagorean's theorem to solve for this side. Okay, so let's do that now. We got sine of 16 over, let's call this value y here, sine of 16 over y equals sine of 90 over 4.6. Okay, let's cross multiply. Y sine of 90. Sine of 90 is again 1, so y times that is just y equal 4.6 times sine of 16. So let's see that in Desmos. And we get 1.2679. Let's just say 1.3. So y is 1.3. That means this remaining piece is 3.7. Now looking at this right triangle, I can use Pythagorean's theorem with this and this to solve for the hypotenuse. So let's do that now. So we got 3.7 squared plus 4.4 squared equals c squared. So after I add these together, I'm going to take the square roots. Let's do that in Desmos. So in Desmos, what I did is I plugged in the unrounded value. So that value, you know, that would approximately 4.4, but I plugged it in exactly, and then I plugged in this one exactly, the difference of 5 and that little side squared, and we get 5.8. So ln is 5.8, and then now we have to solve for the missing angles for L and then for N. So we're going to again use law of sines. We're going to make a little room. So now looking at this entire big triangle, I can say sine of 74 over 5.8 is equal to, let's say L, sine of L over a given 4.6. So now we can solve for L. So we're going to cross multiply. We got 5.8 sine of L is equal to 4.6 sine of 74. Then we're going to divide both sides by 5.8. And then to solve for L, to isolate L, we have to take arc sine of both sides. So I have to take arc sine of this entire quantity. I know we're short on room here, but let's do it like this. And then let's plug that into Desmos. That will give us L. And we get approximately 49.7 degrees. So L is 49.7. And then we can use the triangle angle sum theorem to get the final angle for N, right? 49.7 plus 74, that's 123.7, and then we need what's sup to 123.7, which is 56.3. So there we have N is 56.3, L is 49.7, and the missing side Ln is 5.8. That's how you do it. Boom, done. A pole leans away from the sun at an angle of 7 degrees, so the vertical is shown in figure 27. When the elevation of the sun is 55 degrees, the pole casts a shadow of 42 feet long on the level ground. How long is the pole? Round the answer to the nearest tenth. So the pole is basically this right here, BC. And what we know here is like this angle with the dotted line was 90 degrees. So if that's 70, this remaining is going to be 90 minus 7, which is 83. And then we know that this top value here, just for fun, not like, I don't even know if we need it, but well, actually we will need it because it's opposite 42, but let's solve it anyways. 55 plus 83, that's 138. So the side up here is also 42 degrees. 42 degrees and the opposite side is 42 feet. So now to solve for BC, we can use law of sines. We can say sine of 42 over the opposite side, 42, is equal to, we have to say 55 because that's opposite BC, what we need to find. So sine of 55 over, let's call BC x. Now we're going to cross multiply. X sine of 42 equals 42 sine of 55. Last but not least, we're going to divide by sine of 42 like so. And now we're going to plug this into Desmos. And we get 51.4. So the answer is 51.4 feet rounded to the nearest tenth. Boom, done. So for this question, we're meant to find two things. We're meant to first find the distance from A to the satellite. And then we're also meant to find the vertical distance straight above the ground, which would be kind of like a straight line coming down like this. It's not directly above B, and I can tell that because this is not a perfect 90-degree angle, right? So this would, I'm going to put this in red so you can see it a little bit more clearly. So this is eventually what we'll need to figure out is that red distance where this is a nice 90-degree angle. Okay, so now we got a nice diagram. Let's begin. Oh, and one other thing we have to put in the diagram is A and B. This distance here is 69. Another thing I'm going to do is I know that this is a nice 180-degree angle because it's on a straight line, which allows me to find this inner angle of this little kind of like initial slightly smaller triangle. Because if that's 86.2, inside here, must be 93.8 degrees, right? 93.8 plus 86.2 is 180. Then I can also find this angle up top by using the triangle angle sum theorem. I can add these two together, 83.9 plus 93.8. Boom, add them up, we get 7. That's another 7, and then that's 17. This is 177.7 degrees, which means this angle up here has to be a small little 2.3, because 2.3 plus this adds up to 180. All right, now we can use the law of sines. We can say sine of angle 2.3 over its opposite side, 69, is equal to, we're going to solve for the green side first, sine of that opposite angle, 93.8 over x. We're going to call this x. All right, let's cross multiply. And we get 69 times sine of 93.8 equals x times sine of 2.3. Then we're going to divide by sine of 2.3 like so. And we're going to see what that is in Desmos. And rounded to the nearest mile would be 1,716 miles. So from satellite A, we have 1,716 miles. That's the distance there. Now we need to find this red value, so I'm going to make a little bit of room here. And now we can do law of sines again, but for now this big right triangle, okay? Because I can say for the right triangle, sine of 90, that's the angle there, over the opposite side, which is this. But I'm not going to round it as much. So I'm going to use 1715.555, just to give it a little bit more of an exact answer, is equal to, and then we're going to use sine of this angle because it's opposite the big red angle, the big red side, sorry, which is that vertical distance. So sine of 83.9 over, and we're going to, let's call this y over y. So now we're going to cross multiply. And again, sine of 90 is 1. So literally we just have y equal to 1715.555 times sine of 83.9. Let's plug it into Desmos. And here we get 1705.8 rounded to the nearest mile is 1,706. So it is 1,706 miles above the ground. So those are the two answers. Done. The roof of a house is at a 20-degree angle, which is right here, and an 8-foot solar panel is to be mounted on the roof and should be angled at 38 degrees right there, relative to the horizontal for optimal results. How long does the vertical support holding up the back of the panel, which is this right here, need to be? So what I'm going to do is I'm just going to kind of draw up a little line like this up here. So we got a nice little triangle there. And then I'm going to use this 20-degree angle because the 20-degree angle is interesting because it's also this angle up here, right? Imagine we got parallel lines, and then that's a nice transversal. So they're both corresponding angles, both 20. So if this is 20, then if this entire angle is 38, I know that this little angle in this little triangle is 18 degrees. That's pretty cool. Now, I also know if that's 20, if I were to make in sort of like this imaginary right triangle down here, okay, this would be 90, and if that's 20, this up here would be 70. And if this whole thing is 180, then I know that this little angle here is 110. Look, so now I got 110, 18, add those together, that's 128, which means my remaining angle up here is 52 degrees. Now I got everything I need to use law of sines to solve for x. I can say sine of 18, which is opposite x, so it's over x, is equal to sine of 110, right? Sine of 110 over the opposite side, which is 8. Now let's cross multiply, and we're going to solve x sine of 110 is equal to 8 sine of 18. And then we divide by sine of 110 on both sides. And then we're going to plug it into Desmos. And we get 2.6 to the nearest tenth. And that is 2.6 feet. Boom, done. A pilot is flying over a straight highway. He determines the angles of depression to be to 2 mileposts 4.3 apart. So these two are 4.3 kilometers apart. To be 32 and 56 is shown, and those are angles of depression, right? This is 32, this is 56. And find the distance of the plane from point A to the nearest tenth of a kilometer. So we want this distance here. Okay, so we got enough information to kind of start filling stuff in for this little triangle here. So I know if this is 32 and this entire thing is 56, this little angle in here is 24. Awesome. And then what about this angle down here? Well, this is parallel to this, which means this angle 32 is an alternate interior angle with this. And when you have alternate interior angles for two parallel lines, they are congruent. So this angle down here is also 32. And this is fantastic because now I have the angle opposite the side we're trying to find and an angle opposite a known side. We have enough for law of sine. So let's set it up. We got sine of 24 over the opposite side, which is 4.3, equals sine of 32 over its opposite side, which we'll call x, and let's cross multiply x sine of 24 equals 4.3 sine of 32, and then we're going to divide by sine of 24 on both sides, and let's see what we get in Desmos. And we get 5.6, so the answer is 5.6 kilometers. Boom, done. In order to estimate the height of a building, two students stand at a certain distance from the building at street level. From this point, they find the angle of elevation from the street to the top of the building to be 35. They then move 250 feet closer to the building and find it to be 53. Assuming that the street is level, estimate the height of the building. So let's get a diagram first. So here we have our building, and then here is where the first person is standing. Here is where the second person is standing. And they are 250 feet apart, these two different spots. And then they're both looking at the top of the building. So they're looking like that and looking like this. And the thing is, they said the first angle is 35 degrees. And then as you move 250 feet closer, now it's 53 degrees. And again, we're trying to find the height of the building, which is this value. So what I'm going to do is I'm first going to get this missing angle here, because that angle plus 53 is 180. So that means it has to be 127, okay? And this is pretty cool because I can now use the law of sines to get this side. I just have to first get this little angle up here at the top, but I can get that with the triangle angle sum theorem, because 127 plus 35, that's 162, which means this top angle has to be 18 because they all have to add up to 180. So now I can say sine of 18 over that known side of 250 is equal to sine of 127 over x. We're going to call this side x. Now I could have solved for this side too, but I'm just sort of choosing this side, and you're going to see why. In my mind, I think it's going to be a nice little solution for us. So we're going to cross multiply. We're going to get x sine of 18 equal to 250 sine of 127. Then we're going to divide both sides by sine of 18, and that should give us x. Let's plug it into Desmos, and we get 646.1. So this out here is 646.1. All right, so this is pretty cool because now I have this side opposite this angle, and then I need this side opposite this angle. And of course, what I'm talking about is I'm talking about this big triangle here. Okay, so now I have enough to use law of sines. However, since this is a right triangle, I can also go back to more straightforward trigonometry using just basic sine, because sine of 35 is equal to opposite, which I'm going to call this y, okay, the green, opposite over hypotenuse. And that's what I found. I found the hypotenuse, right? 646.1. So I'm going to multiply both sides by 646.1, and then we're going to get the answer. So y equals 646.1 times sine of 35. Let's plug it into Desmos. And we get 370.5, and that rounds to 371. And since this is in feet, that's 371 feet is the height of the building. Boom, done. A man and a woman standing 3.5 miles apart spot a hot air balloon at the same time. If the angle of elevation from the man to the balloon is 27 and the angle of elevation from the woman to the balloon is 41, find the altitude of the balloon to the nearest foot. So for this one, we got to start by making a little diagram, and we're going to say there's the balloon, and we're kind of making an assumption here that the balloon is in between the man and the woman. So we got the man here looking up at 27 degrees, the woman over here looking up at 41 degrees. And what we're trying to find is we're trying to find the altitude, aka that distance going straight up like so. And the only other thing we know is that they're both 3.5 miles apart. Now, since we're trying to figure this out in feet, just remember that at the end, we're going to have to convert this back to feet. Okay, we're solving in miles, but we will be in feet. Now, what I can do next is I can fill in this angle up top and this angle up top using the triangle angle sum theorem. If this is 41, this is 49. If this is 27, this is going to be 63. Now I can do something else that's kind of interesting. I can call this side x, okay? And I can call this other side here, I can call it y, but I could also call it 3.5 minus x, right? Because the entire thing is 3.5. All right, now I can make some equations here involving this middle side that we're trying to solve for. And I can use standard sine. I don't even have to use law of sines here because we have right triangles. So for example, I can say tangent of 41 equals opposite. We're going to call this blue side y. Opposite over adjacent, which is x. Then I can also say tangent of 27 is equal to, we're talking about this triangle now, opposite over adjacent. So y over 3.5 minus x. So now what I can do to solve is I can use a little bit of substitution. I can multiply both sides by x and then divide by tangent of 41. So x equals y over tangent of 41. And then I can take this and plug it in down here. So I got tangent of 27 is equal to y over 3.5 minus this entire quantity. Then I'm going to multiply both sides by this denominator here. So we got tangent of 27 times 3.5 minus, then we're distributing, tangent of 27 times y over tangent of 41. And all of this equals y, okay? Now what we got to do is we got to consolidate the y's. So I got to add this whole quantity to this side over here. And that's left equal to 3.5 tangent of 27. And to know what this is plus 1, we're going to just use Desmos and then approximate. So tangent of 27 over tangent of 41 is 0.586. So it's going to be 1.586y. And then to last step, we're going to divide by 1.586 like so. And now we're going to plug this into Desmos. And here, instead of using 1.586, I just went back to the more exact value. And then we get 5,936. So the answer is 5,936 feet. That's how you do it. Done. A street light is mounted on a pole. A 6-foot man is standing on the street a short distance from the pole, casting a shadow. The angle of elevation from the tip of the man's shadow to the top of his head is 28 degrees. A 6-foot tall woman is standing on the same street on the opposite side of the pole from the man. The angle of elevation from the tip of her shadow to the top of the head is 28 degrees. If the man and the woman are 20 feet apart, how far is the street light from the tip of the shadow of each person? Round the distance to the nearest tenth of a foot. Okay, we need a diagram. So first of all, we have a 6-foot tall man and woman, and then we need the lamppost that is in the middle. This entire distance is 20 feet. And then we need to look at the shadow, right? So the shadow is coming as this street lamp kind of casts a shadow coming down like so. And same thing coming this way as well. So the shadow would be this section right here, right? And the same thing here, the shadow would be this section. Now for both of these, it says the angle of elevation is 28 degrees. So this angle here, it says from the tip of the shadow up to the top of the head. It's also the same if we drew an imaginary line here. That would be 28 as well. So now what we're trying to find is the distance from the street light, and I'm assuming the bulb all the way down to the tip of the shadow. So we're trying to find this value, which for this triangle, it's the hypotenuse. So what I'm first going to do is I want to solve the length of the shadow because I can already assume that this distance in here is 10 because this is a nice isosceles triangle. Everything is symmetric. So if this whole distance is 20 between the man and the woman, I could say this distance is 10, that distance is 10. I think that's a fair assumption. So now let's solve for the length of that shadow. And the way I can do that is I can use my typical tangent function because that's a nice right triangle. Tangent of this angle that we know is 28 is equal to opposite over adjacent. So it's opposite, and I'll call the adjacent y like this. I'm going to solve for y. I'm going to multiply by y and divide by tangent of 28. So we got 6 over tan 28. Let's plug that into Desmos now. And we get 11.284. So y is 11.284, which means this entire distance is 10 plus that, which would be approximately 21.284. Okay, this is really fantastic because I can use a basic trigonometric function one more time with this giant right triangle to solve for that red portion. And once again, I can use actually, no, I'm not going to use tangent because that would be opposite over adjacent. We need something with the hypotenuse. So what I'm going to do is I'm going to use cosine because cosine of 28 is adjacent, which we now know is this value, over hypotenuse. So adjacent 21.284 over hypotenuse, and let's call the hypotenuse, I don't know, let's call it h. Okay, so that's what we're solving for. And then to solve, we're going to multiply the h across and then divide simultaneously by cosine of 28. So we get h equals 21.284 divided by cosine of 28. Let's plug that into Desmos. So here we got everything plugged in. And instead of using 21.284, that approximation, I did the function that found that value, right? This plus 10. And then we get our nice final answer, 24.1. So the answer is 24.1 feet to the nearest 10th. Boom, done. Two streets meet at an 80-degree angle. At the corner, a park is being built in the shape of a triangle. Find the area of the park along one road if the park measures 180 feet, and along the other road, it measures 215. So here's an example of the park. Here is our 80-degree angle, and then it's saying on one side it's 180 feet. On the other side, it's 215 feet. So we go straight to our area formula for this. It's 1/2, and then times one of the known sides, which is 180, times the other one, which is 215. But then it's important that the known angle has to be right in the middle of these two, which it is. So then we take that and we multiply it by sine of that middle angle, 80. Let's plug it into Desmos. And we get 19,056. So it's 19,056 square feet to the nearest foot. Done. The Bermuda Triangle is a region of the Atlantic Ocean that connects Bermuda, Florida, and Puerto Rico. Find the area of the triangle if the distance from Florida to Bermuda is 1,030, and from Puerto Rico to Bermuda is 980, and the angle created by the two distances is 62. So we got a 62-degree angle here, and then the distance from Bermuda to Florida is 1,030 miles, and then the distance from Bermuda to Puerto Rico is 980. Now, to get the area, we have to have an angle in between the two known sides, which we do, which is amazing. So then we have 1/2 times one of the sides times the other side, 980, and then times sine of that interior angle or included angle, 62. Let's plug it into Desmos. And we get this big number, 445,624. And this is square feet. So that's how you do it. Done. Naomi bought a dining table whose top is in the shape of a triangle. Find the area of the tabletop if the two sides measure 4 feet and 4.5 feet, and the smaller angles measure 32 and 42 as shown below. So the thing is, we need this angle. We need to have the included angle between the two known sides in order to use the formula. But we don't have it, but we can deduce it because these two add up to 74 degrees. And therefore, this would have to be 106 because all three angles need to add up to 180. Okay. Now we can say 1/2 times one of the known sides times the other known side times sine of the included angle, and let's plug that into Desmos. And we get 8.65 to the nearest hundredth, so that would be 8.65, and again, it's feet squared because that was in feet. That's how you do it. Done. I hope you guys enjoyed this video, and if you did, please click that like button. If you want to see more from the Scalar Learning channel, make sure to click subscribe. Thank you guys so much for joining, and I'll see you in the next video. Take it easy.